worked in my office, but then I wasn't attached to a projector. And if it doesn't work, we'll figure it out. So I want to, why? Oh, God. Okay. Let me see if I can get this going. And extend. For some reason, it's thinking my tablet's the desktop, not this. Let me see. What's happened? Where'd this go? Oh my God. Okay, so what happened to my, I have this beautiful video I was going to show, but it's not, oh crap. Okay, I think I'm not going to, I think I'm having enough trouble just with what we have. So let's just look at, let's see where this goes. Okay, so this is weird. So the PowerPoint is not showing on Teams, I bet.
Are you sharing the tablet?
See, here's the tablet. So typically the tablet and that are the same, but it's not doing that. So typically I share the tablet on Teams and then that, and now I can't even get my cursor back. Oh, okay, what direction?
You want the computer and the tablet to show the same thing?
I want the screen and the tablet to show the same thing. So let me just see if I can figure out where my cursor is. Oh my God. Sorry about this. Oh, here we go. Okay, here's my cursor. So let me try this. Let me see what I can do. Display settings. So okay. So what does it mean that the 2 is, like a 2 is showing up big? Because typically 1 shows up, so detect, didn't detect, identify. So 1, 2, and then my tablet is 3. So my tablet's 3, my computer is 1. So what I'd like to do is extend, let's see what happens if I duplicate. Okay. Well, this is a little better because now, oh, okay, I think I can make this work. I think. We'll see. And maybe I'll try the video in a moment. Okay, so not exactly what I had hoped for, but let's give it a go. Oh, now it all seems to be working. Okay, so let's talk about powder metallurgy. And so I have a short video that I was going to kind of show from the Powder Metallurgy Association, and I was going to, let me just go ahead and get this going as well. Where Teams has gone, and if everything is good on Teams, make sure my audio is right. Device settings. Okay, so a little, oh no. Let me get my PowerPoint back up. No, here we go. Okay, not totally sure what happened, but we'll make the best of it. So in powder metallurgy, we start with metal powder, and that's where we get the parts. So we have casting where we shape liquid. We have deformation where we shape solid powder. And then we have, or we solid metal, and then we have powder metallurgy. And so here we have examples of a number of powder metallurgy parts. And my cursor's not work, or my pen's not working, and I'm just gonna, like, maybe at the end figure out why. But here we have a number of different powder metallurgy parts. Some of them are very small. Some of them have a lot of intricate detail. This part down here in the lower left is kind of interesting because it has square holes and round, and all of that is what we would call net shape. So coming out of the press, this is what we have. Oh no. Okay, I'm going to pull up a different PowerPoint because my plan was that I'd write on my tablet and we'd talk about it, but since I don't know how to write on my tablet at the moment, that's not going to work. So you can write these things down as we discuss it. So in powder metallurgy, we start again with ceramic or metal powder. So a lot of ceramic parts are this way. And then we can mix them together. It is what we call a solid state process, meaning that we don't melt when we do it. So there are some really kind of cool product groups which are really good for powder metallurgy. So one of the things that we'll talk about as we go through is powder metallurgy parts always have porosity. We can't get rid of the porosity. However, we can control the porosity. And you will notice that one of the parts look like a filter. And there are some really cool reasons why we might want to have a part that has porosity that we like. For instance, in the medical field, if you have porosity that is about the right size for a bone cell, that will help bone grow into the implant. We also could have a filter. We also might be able to pull oil into the part and sort of have a self-lubricating part. So there are some applications where being able to have a porous part is good. We can get really complex parts. And so we say that these are net shape, meaning the part that comes out of the press doesn't need machining. We could also look at difficult to machine materials. So if you have something that's very hard or brittle, if you can actually press all the holes in complex shapes, that would be great. If we want to have two distinct materials, like a carbide and a metal, or in the case of one of my examples, and I'm just going to go up to the example, down here, these are copper and graphite electrical connectors. And the copper and the graphite stay as copper and graphite, and that really helps the properties.
And then for some materials, we get superior properties. And that goes back to like the cooling rate of the metal when it's formed. Okay, so there are some really cool product groups. Now, I think it's important to recognize that when we say conventional powder metallurgy, that's going to be the process by which we're talking. These parts will always have some porosity. The porosity, we can control it, but we cannot eliminate it. Now, again, there are some advantages, filters, self-lubricating parts, and also in some cases, we might be able to specifically match the property, for instance, the ability to damp and also thermal expansion, because, you know, porosity is basically air. Generally, porosity is considered to be a negative. For powder metallurgy parts, we recognize that the strength and the mechanical properties are not as good as wrought. When you start having holes or voids, your properties just aren't as good. And hardness does not correlate to strength. So that's one of those aspects of powder metallurgy parts that if you're switching a wrought part to powder metallurgy, hardness no longer tells you what you need to know. But if we kind of think about it, thermal conductivity is reduced with porosity. And, well, how does that matter? That would matter because if we have to heat treat the parts, they're going to heat and cool in a slightly different way. And then corrosion resistance is reduced as well. Now, we'll talk about ways that we can fix some of these, but I think we really kind of need to recognize that with powder metallurgy, we always have some density issues. Okay, so when we talk about powder metallurgy, we have 4 basic steps. And oh, I so wanted to show the video for this. Well, we have powder production, and we'll look at all of these terms and describe them. But typically in powder production, we can make it in a number of different ways. Atomization is the most common. And in atomization, just go to the next slide. In atomization, we basically melt our metal if it's a metal that has reasonable melting characteristics. And then we basically pour it into a chamber, and then we blast it with either gas or water. So we have our stream of molten metal that we then blast with either a gas or water that breaks the molten metal into droplets. Those droplets solidify very quickly, and therefore we have our powder. So most metals are made by atomization. Obviously, your very brittle or your ceramic powders are not, but atomization is the most common way. Okay, we'll talk about some of the powder characteristics in a moment. And we'll look at some examples of some powder as well. We also have to, if you kind of think about it, if you take sand and you compact it, does it hold together? No. Will is shaking his head no. Well, neither does metal powder. If I took my metal powder and I just poured it, it's not going to hold together. Also, if we have metal, when we're compacting metal powder, it also is going to have a fair amount of friction. And so as we're sort of moving the powder in the die, there's friction. So we need to add things to the powder. So in the blending and mixing step, we either mix different powders, so if we want to get different sizes, or we can mix different compositions like our graphite and our copper, and then we also put in processing aids. So these processing aids could be lubricants, binders. One of my favorite is a deflocculant, basically something that keeps it from clumping. So we will put in processing aids that we then have to take out. So again, we often put in a binder. Then we compact this powder mixture, and we'll come back to this term. But when we have our collection of powder particles that are compacted into the shape, we call that a green compact. Green in powder metallurgy means compacted, but not sintered. So it's a collection of particles. And then our sintering is where we let diffusion turn our collection of powder into a metal part. Okay, so we have our atomization, and let's kind of consider some of the things that we might care about in terms of the powder. One is the powder shape. The powder can be spherical, so nice little spheres, or it can be angular, so it can be have a lot of various little ledges. We've seen that term shape factor before. Generally, a shape factor is going to somehow characterize the surface area to the volume. Sometimes, and so the higher the shape factor, the more surface area we have. Spheres have a low shape factor. As you start to get to more flaky particles or feathers, that goes up. We also are interested in the size and the size distribution. So I think I've mentioned that I worked in the diamond making business, and one of the things that I worked with was our tooling. And our tooling was made by powder metallurgy. It was a cobalt and tungsten carbide. And so one of the things that we were very interested in with our supplier was what was the size distribution of the tungsten carbide powder that went in. So is it a normal distribution? Is it a Gaussian? What's the standard deviation? So those are things that influence the final product, and then the overall size. And then just the chemistry. Sometimes we have alloy powder, and sometimes we have pure metal. So sometimes we actually mix pure metals. Most of the time, we actually create the alloy. So let's look at some pictures. So I have some different, this is a copper, this is a steel, and over here we have baby powder. So the powder that I have, it's a little bit coarser than baby powder. It's not as coarse as typical sugar. So kind of gives you a little bit of an idea of what we're talking about there. But again, this is a pure copper and this is an alloy. So want to talk about compaction. So when we compact the powder, what we're doing is we have our powder with its binder and lubricant, and we're going to put it into a die, and then we're going to compact it. Now, density is very, very important. And so in compaction, we're getting the basic shape, but we're also establishing the green density. So the green density is the density of that compact. And that's really important. So, man, I so want to write. I wonder if this works. Nope, I didn't think so. Oh, I wonder if I can do it. Nope, that's not going to work. So when we establish our green density, we recognize that for powder metallurgy parts, density controls properties. And the density of our compact relates to the density, the final density, and the density that we achieve is related to pressure. Now, how well does powder transmit pressure? What do you think? So if I have a large column of powder and I apply a pressure at the top, are we likely to see a high pressure in the center? May not have thought that much about it. Powder does not transmit pressure well. It really doesn't. It's like fluid transmits pressure. You know, I mean, that's the whole purpose of hydraulics, right? You apply a pressure and that pressure goes through the fluid. Powder does not transmit pressure well at all. And so when I come back to this statement where I say pressure is important in green density. So we really have to kind of think about this compaction state. We're getting the shape, we're getting the green density, and the density of this compact is very, very important for the final property. And the density that we can achieve is related to the compacting pressure. So here we have, you can see that we've got 2 coppers and 2 iron powders here. And we're looking at pressure versus density. And we see that as the pressure increases, the density is increasing. So this graph just shows experimentally that statement that higher pressure gives us higher density. And so we'll talk about how this pressure density influences both some of the design features of the process and then also what types of process variations we can achieve. Okay. We also are going to provide adequate green strength. So green strength is the strength of the compact. It is only important for handling. And then we also in compaction need to get powder to powder contact. So here are some examples of some green compacts. If we kind of look at it a little closely, it doesn't really look like a metal. If I had it in class on a typically what I would do is I'd pass these, well, I might not pass these around because they're very fragile, but like if we kind of drop it, it doesn't have the sound of a metal. It doesn't look like a metal. It looks like a collection of particles. They're very fragile and they break very easily. So the green strength is relatively low. but it's the basic shape of our final product, and whatever the density is, will affect the final properties as well. So if we kind of think about this, powder does not transmit pressure well. Most cases, we're pressing from the top or top and bottom. And so if we have a thick part, we're going to have a pressure variation and a density variation. And so again, if we have our pressure gradient, we'll have a density gradient, and then we'll have a property gradient. There are 3 types of pressing that we can do. The most common is the single action. So the single action is where we fill the die, press it from the top, eject the part. In that case, we have the highest pressure at the top, lowest pressure at the bottom, and we have the properties that way. If we start to have thicker parts, we can have a double action press, where we've got the rams approaching from the top and the bottom. So we're pressing from both sides. Here we cut the density variation in half, and the lowest comes in the center. And then the final one is one that we call isostatic pressing. Isostatic means it's uniform in all directions. And if you're thinking, oh, like, how do you do that? That sounds a little more complex. It is. So if we look at like a standard compaction, we have our die, and we have our punch, and here's our pot. So this is a double action. So we fill upper punch, lower punch. After pressing, the lower also ejects. Isostatic is where we are going to, we put the mold is oftentimes a bag or a container, and we put the powder in there, and then we have a fluid that applies the pressure from all directions. So if we're talking about an isostatic pressing, we're usually doing this within a pressure vessel and a fluid. We can do it cold, or we can do something that's called hot isostatic pressing, or HIP. If you're thinking that this increases the cost, it does a lot. But again, it does help us get more uniform properties. Okay, hammering, or kind of continuing with this idea that final density makes a difference. Here we have final density versus properties. So you can see that strength, conductivity, and ductility all increase with density. So that means that, again, your final product is very dependent on density. Okay. I want to see, I'm getting daring here. I want to see if I can make this happen. Okay, I'm going to unshare this. I just want to see. Okay. No, it's not working. Okay. It is, but it's on the wrong place. Okay. I was hoping maybe I could get that figured out because I'd really like to show that. Okay. Can't quite do that. Let me find my team. Share this. Okay. So we have our compact, and now we're going to go into diffusion. We recognize from 321, we talked about this idea that the system wants to get rid of surfaces, grain boundaries, dislocation. So we have all these small particles, all those surfaces, they're in contact. There's a huge driving force for that, for those surfaces to be removed. That's what happens in the sintering process. It is a solid state process, meaning we don't melt. We are at a high temperature. We're about 0.7 to 0.9 of the melting temperature on the absolute scale. The process itself takes anywhere from 10 minutes to 8 hours. The larger the part, the thicker the part, the longer it takes. It is always done in a controlled atmosphere. It could be a vacuum. It could be a protective environment, argon, nitrogen, or it could be a reducing atmosphere. And what is a reducing atmosphere? If we talk about a reducing atmosphere, what does that actually mean? We talk about oxidation and reduction. You remember from chemistry what we're talking about? I love that. Don't make eye contact with her, don't I? Right. So a reducing atmosphere is one that's a little more active. Oxygen is the problem. When you have metal in the presence of oxygen at high temperature, you can easily get oxide. Metal to metal will bond very well. Oxide to oxide does not. It doesn't bond as well. So a reducing atmosphere generally is going to have some hydrogen in there, and it actually would take an oxide, any oxide that's there, and remove it from the metal. So anyways, just a little bit of chemistry to throw in on here. But sintering is never going to be done in air. It is always going to be done, again, vacuum, purely protective, or maybe a reducing. So the green compact becomes the metal part. So that collection of particles, becomes our part. It is a diffusion process, and there might have been a couple questions in 321 about this process, like that time-temperature relationship. There are 3 stages, and they all occur with the protective environment. And let's look at these 3 stages and what happens. So the first is a burn-off stage. Now, sintering occurs either in a conveyor oven or furnace, where the parts move through the heating stages, or it happens in what we'd call like a bell furnace, where we put the parts in a furnace, and then we cycle the temperature within the furnace over time. The green parts, now let's kind of think about this. The green parts have a lot of density, have a lot of porosity. They're relatively low strength. The thermal conductivity of the green part is substantially less than the thermal conductivity of the metal. They're weak, we need to really slowly increase the temperature. So the preheat stage does two things. It slowly gets us up to temperature, and we have to go in a very slow way in order to not have thermal shock. And that would be minimizing those thermal stresses. Also, we put in binders, lubricants, flow aids. Those generally are going to be somewhat volatile organics, which we need to burn those off. So we need to allow time for any of those aids to volatilize and for that gas to safely, gently leave the compact. So this is really important. Then once we're at our high heat, that's where we actually get the bonding. That's where the diffusion occurs. And so again, when we're at that high heat, that bonding, we see that atoms are going to move from one particle to another. And so we're going to start to eliminate the surfaces. And then we're eventually going to see there's going to be this reduction in porosity, increase in density during sintering. So it is pure diffusion where we see atoms kind of move from the particles into these spaces between. And then once we've fully sintered, we're at a very high temperature. We do need to cool down in an organized, controlled fashion. We can cool down at a faster rate than we can heat up, but we still need to cool down in that controlled atmosphere. Okay. So that's our kind of the conventional process. Make the powder, blend, compact, sinter. What we get out of the sintering furnace is generally the shape of the parts with minimal machining. Okay. So what I want to do is go back and look at some of the shapes of these parts. Kind of move, see if I can move this. There we go. So let's kind of think about one of the things that we may notice about this. A lot of these parts are fairly thin. They're they're very complex in what we would consider the pressing direction. And we can have an amazing amount of flexibility in that pressing direction. Powder metallurgy parts work very well if they're thin. So all of these parts here, there was no machining. These parts came out of the sintering furnace, and this is the shape you can have. So that is really exciting that we can, with powder metallurgy, press in and create holes and voids and a lot of complexity. We also notice that a lot of the parts do tend to be thin, although they don't have to be. Okay. You're going to see like, yeah, this density talk again. We got it. Oops. Am I still sharing? Oh no, what did I do? I think I did something I didn't want to do. There we go. Okay. Oh no. I think I've been sharing the wrong slides to the people on Teams. Oh man. Okay. Anyways, density. Conventional powder metallurgy parts that we get from the sintering are going to have 5 to 25% porosity. We usually, like if we're on the high side of the porosity, it's because we've intentionally made the porosity. But usually we're going to be, you know, if we're producing parts where we don't want porosity, we're usually in the 5 to 8%. That's just, it's there. We recognize that we will see a reduction in strength, a reduction in ductility, a reduction in toughness, a reduction in conductivity as well. And again, we can control the size and shape of the porosity, but we can't eliminate it. We can work with ways to have the to deal with it, but we can't get rid of it. Again, we talked about some of the properties for PM parts that vary with density. And again, strength, ductility, toughness, conductivity. What we will talk about tomorrow is how we can minimize the negative consequences of the porosity with some secondary operations. So some things that we can do once we sintered. Okay, this is where I'm going to stop for today. I am going to stop the recording.